So today we are going to talk about the intramolecular Diels-Alder reactions. Okay, these are the examples I have taken. So in these examples we can see how intramolecular Diels-Alder reaction will goes. First we will see this first one. So here we have these examples you can find in Carruthers book. So here this bond goes here, this comes like this, and this goes here. The product what we will get here, if I remember. Now the stereochemistry of this CO2Me and this hydrogen, because these hydrogens are here, Bridgehead hydrogens are there. This stereochemistry is important. So now you can see here, this is the E stereochemistry and this is also E stereochemistry, and you can now we focus only on these two hydrogens because these two hydrogens are Bridgehead hydrogens here. So these two hydrogens, this hydrogen is facing downwards and this hydrogen is facing upwards, right? So they are in a opposite direction. So one hydrogen is coming like this, another hydrogen is going like this. They are in opposite direction. So because of that reason, in the product also they should be in a opposite direction. Okay, now this hydrogen and this CO2Me, they are in the same side. This is left hand side and this is also left hand side. So whatever the position of this hydrogen is there, same position CO2Me also comes. Okay, so this is a major product here. So there one more product also forms here. So this is another product here we'll get. So there is a condition at 150 degree temperature. This is 65%, 60% will come, and this will be 40%. At if you will use the Lewis acid, you will get 100% of this one, and this is 0%. So what is the Lewis acid doing here? So there are three factors, main factors for Diels-Alder reaction. The first one is a Lewis acid catalyst. The second one is temperature. Third one is solvent effect. See, these are the three important effects which we have to discuss in the Diels-Alder reaction. So when we have a Lewis acid, this Lewis acid goes and binds to the dienophile oxygen. So whatever the dienophile, let's imagine that we have this reaction. So here this is diene and this is dienophile. So Lewis acid goes and attacks to this dienophile carbon. So in the Diels-Alder reaction, the diene should be electron rich, the dienophile should be electron deficient, right? So when this Lewis acid goes and attacks to this dienophile carbon, so it will take some electron density from this oxygen, and it's making a dienophile more electron deficient. So because of that, the rate of reaction will increase. Because of that rate of reaction is increasing, so we are getting 100% of product, 100% of conversion. So how much this is electron deficient, that much. If it is more electron deficient, we will get more product, like that. And we can explain by using temperature and the solvent also. Like this temperature solvent effect we mainly see in case of endo rule is there in the Diels-Alder reaction. Okay, according to endo product is a kinetically stable product, exo product is thermodynamically stable product. So but in Diels-Alder reaction, endo product is major. But if we increase the temperature, the amount of endo will reduces, but amount of exo will increase if you increase the temperature. So there are many examples in Carruthers book, you can find also for this one. Why? Because thermodynamic product means what? The product which forms at a high temperature. Kinetic product always forms at a low temperature. So if you are increasing temperature means the exo product will increases, because exo product forms at a high temperature. And solvent also, some solvent, like if you use the methanol and ethanol, alcoholic solvents, so you exclusively gets endo product. If you use triethylamine, then you exclusively get exo product. So these are the three important factors like in Diels-Alder reaction. We have to read this also. Just remember Lewis acid. If you use the Lewis acid, okay. Another thing, why the rate of reaction is faster in case of Lewis acid. So when it's become electron deficient, the initially LUMO is here. This is the LUMO of dienophile. So after Lewis acid coordinates to the this oxygen of this dienophile, the energy of LUMO is decreasing. So once energy is, you see, initially this is the HOMO and this is the LUMO. When we don't have Lewis acid, after we have Lewis acid, the energy is decreasing between the HOMO and LUMO. That means rate of reaction will be faster. So this way also we can explain. Okay. So this is the now we are talking about the intermolecular cell reaction. So because of that, I have explained these things. Just remember that these two hydrogens are in opposite direction. So in the product also it should be in opposite direction. Okay. And next, we have another example here. So this one we will write it in the like this way. If you write any whatever they have given, if you write it this way, you can easily predict the product. I am writing this like this. Okay, and here see, E stereochemistry is there. This should be like a E. Imagine that this comes CO2Me here this side, and here one hydrogen, another hydrogen is there. Now how many carbons? 1 2 3. 3 carbons are there. 1 2 3, and this direct bond. So now and this bond, sorry, no, not this way. This way it goes, this comes here. Now we have a 1 6-member ring, and this will be 1 2 3 4 5-member ring. 1 2 3 4 5-member ring. Okay, now the stereochemistry we have to identify. So this is the, here Bridgehead carbon is this one, right? This one and this one. So this hydrogen is going this way, this hydrogen is going above like this, and here this hydrogen also going in the same direction, right? So this hydrogen are the bridging hydrogens here. They both are in the same direction. This hydrogen is going upward and this also going upward. So because of that, both comes the same side. Now this CO2Me and this hydrogen, they are also in the same side, right? That means it will be CO2Me. I will write this, I will explain it again. So here these two hydrogens are bridged hydrogens, these bridged hydrogens. So here this is going above the, means upward direction, and this is also in the same direction. Because of that, they both came in the same direction, and this hydrogen and this CO2Me also, they are cis to each other. Because of that, they are cis to each other. So this is the product in this case. And next we have another example. OR here. This one here. This goes this way and this comes this way, Here we have a 6-member ring and one 5-member ring. 1 2 3 4 5. 1 2 3 4 5-member. Okay, now these two hydrogens and these hydrogens, you can see here this hydrogen is coming down and this hydrogen is going up. So these two hydrogens are trans to each other. Here these two hydrogens are cis to each other. Here these two hydrogens are trans to each other. Because of that, they will come as a, if it is above the plane, and this should be below the plane. And now this hydrogen, this CO2 are in the same direction, cis to each other. Since it is a backside, CO2 are also comes backside. We just need to see that whether these two hydrogens are facing opposite direction or same direction. So here it is same direction, we got cis product. Here it is opposite direction, we got a trans. And then say Me3 methyl. So this goes like this, this come here, this comes here, so that we will get two 6-member rings here. Now here the bridging at bridged carbon, one place we have methyl group, another one we have hydrogen. Okay, here this methyl group is coming down and here hydrogen is going up. Methyl and hydrogen, they are trans to each other, right? So because of that, it has to be trans stereochemistry. Okay, this will be OSIMe3, and further if you do hydrolysis, it will get converts into this OH. Okay, and next like this. So when we heated this one, this SO2 will get eliminated like this way. And here we have a dienophile. Now the Diels reaction takes place here. So now this will be a aromatic ring. Okay, now we have to see the stereochemistry. like this first we'll see stereochemistry at these two bridge carbon. So here this hydrogen is here, and here see this is the methyl group. This is the methyl group above the plane, above the plane. That means the hydrogen which is present here, carbon valence is 4. This is already 1 2 3, so hydrogen is there. So that is a, it will be like this. Okay, so these two are trans to each other, these two are trans to each other. So if you take this one below the plane, and it should be above the plane. Okay, and further like this methyl group is above the plane, this methyl group is above the plane. So here this group we have above the plane, and the hydrogen which are present here, that is below the plane. So that hydrogen comes here. So this is the stereochemistry. See, these two hydrogens are facing up trans to each other. Because of that, in the product we got them in the trans, and here this methyl group is above the plane, so this will keep it is above the plane only. And here one hydrogen is a like we have 1 2 3, and the hydrogen which are present here, that is below the plane, that comes out below the plane. So this is the stereochemistry in this reaction. And we have like another example. So in this case, like here like this goes here, this double bond comes here, this comes like this, so that we'll get NR here and double bond O, and here further we'll get another 6-member ring. Here we have a CO2 Me. Okay, now see here, so this hydrogen is coming down, and this see this is a bridge here, right? Now like it has to be like this. That means these two carbons are present here and here. So this is coming downwards, down, and here actually the orientation whatever I have written, it's wrong. It has to be like this. Okay, like okay, you take in this same way only. So it's coming downwards and it's going upward, right? See, it means they are in the trans to each other. If you take this one below the plane, and you should take these two in the above the plane. Okay, and now I will write it whatever given in the book, that orientation I will write now. In the book they have given like this. and here double bond O. So if you see here, this hydrogen is facing downside and this hydrogen is facing upside, and this group, whole group, is facing downward. Now we have to focus on this hydrogen and this group. They are cis to each other. If this is below the plane, and this should also comes below the plane. This is the product. And we have another example. SiPH2 CO2Me. So here we have one condition, like in Diels-Alder reaction. If you see the regioselectivity in the Diels-Alder reaction, when we have a like this trans compound, so this is E and this is also E, right? So in this case, these substituents will come cis to each other. So when we have a E and Z, in that case the substituents, in the product, the substituents will come trans to each other. So this condition we have to apply here, because this is the E and this is also E, so they both are facing opposite direction, and in the product side they has to come in the same side. So if you take methyl here above the plane, and oxygen also should be above the plane like this, and CO2Me comes here. So this is very important. When we have a both E substituent in the product side, we will get cis stereochemistry. When we have one E, one Z, in that case trans stereochemistry we will get. And one last example here we have. This is upon treatment with N-beta lithium and this Gignard reagent, we'll get Mg C double bond CH2. So here also same. Here also we have a E. Here also we have E. That means these both should come same side. Okay. So this is about the intramolecular Diels-Alder reaction. These all examples you can find in the Carruthers book.